Now we can also define the tangent line in Mathematica. That's this capital L function that's defined on the page here. And again, if you haven't already, I would encourage you to pause the video and actually do this in Mathematica. So we have our point of interest, the tangent point at a comma f of a, and we already defined f of x above to be x minus 2 quantity squared. So, for example, we define this capital L in terms of x and a, so we're going to get a function of x when we specify for a the x-coordinate of the point of tangency. So what we have here is the tangent line to our function f, that's x minus 2 quantity squared, at the point of tangency x equals 1. Or at the point, if we use both coordinates, 1, 1. Okay, so now I've given you the code to create this table so that we can see delta y and dy for different values of dx here. And of course you can copy the code, but it would be a good idea for you to stop for a while and sort of think about and understand where the code is coming from and why it gets you the table below. But first of all, let's walk through the line that relates to the example we had done. So first of all, I'm at my tangent point 1, 1, and when I make my dx negative 0.1, which I had done in the example, my x-coordinate now moves from 1 to 1 minus 0.1, and now my x-coordinate's at 0.9. Okay, then, using the same color scheme we had before, my y-coordinate was at 1 on the tangent point, and then I wind up on my function at 1.21, that's what we said earlier, because my delta y value, which tells me about, right, here's delta y, and here's dy, the differential. My delta y value change in f is 0.21, so for a 0.1 unit change to the left on x, my change in y on the function is 0.21. Now I can also think about, I was on the tangent line y value of 1. So remember, when we're at the point of tangency, that is the one point that is both on the function and on the tangent line. And when my x-coordinate moved 0.1 units to the left to 0.9, my y-coordinate on the tangent line moved up to 1.2. My dy differential value was 0.2. So in this table, I can see all the little pieces, all the moving parts, right? And of course, we could look at other lines as well, and hopefully you could walk yourself through any other row in this table to understand what it's telling you. Notice the first two columns are always the same. In other words, my tangent point at 1, 1 is not changing. The rest of the table explains how much my x is changing, what my new x-coordinate is, what my new f of x value is, what my new L of x tangent line value is, how much my f changed, that's my delta y, and how much my tangent line value changed, dy, which again is an estimate for delta y. So I could put approximately's in here, or I could put approximately's here. So remember, we're using the tangent line as an estimate for where I would be on the function. And as long as I stay pretty close to the tangent line, I'll get good approximations. Now you notice as we work our way from the top of the table to the middle, where my dx is 0, so I'm at the point of tangency. I haven't changed my function value. I haven't changed my tangent line value. I'm staying in the same place. As we move from the top of the table down toward that, the difference between f and L is getting less and less. My delta y and dy values are getting closer together, right? My dy value is getting closer to 0. As I work my way from the bottom of the table towards the middle, the same thing. The difference between the f and the L is getting smaller. The difference between the delta y and the dy is getting smaller. Okay, and then if we look at the function f of x graphed along with the tangent line, now here again, based on my scale, I can find x values at 0.9 and 1.1, and when I go up to the curve, that's kind of the overlapping interval where I can't tell the difference between the orange and the blue, right? Once I move beyond, further from one than that on either side, then I can start to see the function and the tangent line separating from one another, right? So, and that of course depends on the window, how much over what input interval you can't distinguish between the function and the tangent line. In this window, the function f of x and the tangent line L of x are indistinguishable. That's a big word. You can't tell them apart. For x equal 0.9 up to x equal 1.1, right? If I change my window settings, I could change that x window, and where the overlap would appear might look different. Okay, but basically that is these rows of the table. Let's see, I didn't go down far enough here, hang on. Right, basically these three rows where my delta x is between negative 0.1 and 0.1, or my x values are between 0.9 and 1.1. Graphically, in the window I have here, I cannot tell the difference between the tangent line and the function over that x interval.